Make sure you turn your cell phones off. I'm going to do that while I'm talking to you. I've got my name tag today, so I'll remind you to wear your name tag and check the roster. Looks like our group is thinning a little bit as we get to the end of this session, which is typical. We got Wisdom Wednesdays coming up tomorrow, and this is the announcements I'm reading here that were left for me is for last Wednesday, so we'll dispense with that. This is a kind of an interesting picture to me. I designed aircraft windshields and tested them and produced them for 25 years. I always had a concern of what if they come up with enough technology that they don't need pilots, and if they don't need pilots, they don't need windshields. And so I'm not worried about windshield production anymore. But anyway, we did I did a survey last week. And there was 12 participants. I asked whether they would board a commercial flight without a pilot, and 9 said no, 2 said yes, 1 said maybe. 1 actually checked no and said maybe, and another one said not today, not at first, maybe way in the future. And Jim Holmes has skin in this game, and he's a retired Delta pilot. And I asked him, and he said, no. He said, there's too many things that could go wrong. So we'll kind of get into that. This was put on this deal, and my specialty in doing presentations is to plug a DVD in and then kind of answer questions, maybe. So this is a little different for me, so bear with me as we go through this. But I didn't do this presentation. This was done by my brother for Duke, Ollie. He's also an Auburn grad. He graduated in '57, which was a pretty important year for Auburn. He didn't take a lot of credit for it because he was co-oping most of the time. But he got in his 1949 Chevrolet and drove west and never did return to Alabama. Had a short stop at Chance Vaught in Texas, and then he moved to Phoenix, Arizona, where he designed autopilots, which is kind of the entries that you see here. And then he went on to Hughes Helicopter, where he was a manager of avionics for the Apache helicopter. Then came back to Texas to be president of Aerospatiale Helicopter. So anyway, he was the smart one in the family. So the intent of this thing was that, and we'll skip some of these slides, but the intent of this course was to have maximum discussions, minimum lecture. He was looking for opinions from everybody, and there's no, he didn't come to any conclusion here as far as which one. You just got to come to the conclusions yourself. So even after 352 slides, there was no conclusion there. So he actually had people do research. Anyway, let's talk about, and we already talked about your thoughts on boarding a plane without a pilot, and if we'll ever get to that. I think, Mike, you were one of the few that said that you would board a plane like that. Any comment on that?
I have a right to be smarter today than I was yesterday.
Okay, so you decided it's no now?
Well, I thought about it a little bit. My brother's a pilot. Well,
Yeah.
he was a pilot. And I had the opportunity during the time he was doing a cross-country flight training for his private pilot's license to run out of fuel in an airplane with it.
Yikes.
And I would be, well, we were pretty desperate. We did manage to find an airfield. But I would wonder what a computer would do if something like that happened.
Yep. We're going to get into that.
It might be that the computer was just going to run out of gas. It would know that it was getting low on gas.
It would have detected it. Actually,
Yeah.
this was, they had a problem with the way the carburetor was seated or something like that. The computer probably would have detected that it was using fuel at an unusual rate.
Yep. Okay, so he said for 2 years he's been asking people whether they'd fly in an aircraft without a pilot, and Henry, who is a retired accountant, said, "Are you kidding me? No way." Abby, his teenage daughter, says, "Oh well, if everybody else does it, why not?" Abby's now a sophomore at the University of Maryland. Wally, who is a pilot for a major airline, said it seems inevitable, many issues to be dealt with first, the devil's in the details. So the course plan is to, the other thing is that I need to decide whether I want to present this next year to Ollie, so that we'd do 10 sessions instead of 1. So I need your input. I need to decide myself whether I want to do it, but secondly, I need your input on whether you think it would be worthwhile and everything. Another point, Duke Ollie is larger than Auburn's, which is not unexpected. Probably about 2 or 3 times larger. They charge for each class. So taking this class would cost $90. I think there would be less people sitting here today if that was the case here. The other thing about the people there is that they have very little interest in technical issues. So he presented this, I think, with 6 or 8 people, and then a year or a little later, the next year, offered it again, and not enough people signed up to be worthwhile. So anyway, there's not a lot of technical interest there. Okay, so we're going to look at early examples of automation, motive forces behind pilotless transport, a few of the details, specific events which pilots managed in an extreme emergency and saved passenger lives and were a major contributing cause of the crash, or were a major cause of the crash. And then order in which a few full automation might be introduced. Jim, you recognize this cockpit? Is this anything? Okay, this is a,
That's an Airbus because it doesn't have a wheel in the middle.
Yep.
Joysticks on the right.
yeah. This was just talking, they were going to have a special guest that particular day. I've already seen that one. Okay, automation's been done before. You see there is an elevator operator. We've got mass transit type trains, and now we've got some driverless autos running around with some degree of problems. Elevators start at the beginning. First passenger elevator was in 1870. It was in a New York office building. They made safety improvements. In 1900, the first operatorless elevator. Public hated it. They removed it from service. 1919, special criteria was established for female operators. And you can see that. I'm not going to read it to you. And that's a picture of the Marshall Fields Training School.
Was that something, I mean, they had to be licensed to go to school to learn to operate the elevator?
I think so.
When did women, let women start driving cars?
You know, this is not about cars.
Is that beyond the scope of this board?
Yeah, that's it. That's the word I was looking for. Quit asking questions, Jim. Okay.
Well, we got a bunch of them.
Okay, good. 1945, the year I was born, elevator operators, there's a strike in New York City. 1.5 million office workers couldn't get to work. City ground to a halt, lost $100 million in tax revenue. Industry responded with safety improvements, full automation, persuasive ads, soothing voices. This is an automated elevator. Please press the button for the floor you desire. Buttons were added. They've got an open door and push for alarm and press to call and close door and stop. Okay, so what are the motives behind pilotless flight? We could cut the payroll, maybe add a few more seats. Say what?
I don't know how they could add any more.
Oh yeah. If you don't, I mean, you take the weight of the windshields out from the front. The 747 windshield weighs 175 pounds. That's another person. So you've got, if you look at the number of pilots for American, Delta, and United, 14,000, 12,000. You would eliminate, an airline would eliminate 14,000 pilot jobs.
Can't even get out of Walmart, let alone.
If you look at cost of the pilots, I think this is cost.
One airline.
Yeah, that's
Billion for one airline.
right.
So we're talking about close to $10 billion a year.
Right. Well, I'm not going to go through all these calculations, but for 14,000 pilots, he's saying you could save $3 billion a year.
Would you, that means you eliminate the co-pilot also? And
Yeah, that was, yeah. Yep. I don't think that, the pilotless plane, I don't know. I don't think I've got that in all this.
It would be a whole lot more than it is right
No,
now. You're gonna have some redundancy, but,
Right.
Most of this stuff is already in the airplane.
Right. Autopilot, sensors, and that type of thing. The potential to add revenue seats. So basically, over 24-hour period, you could add 15 to 17 seats based on removal of the pilots. And a weight reduction. He's got the weight of those windshields up front. Those were Airbus windows. I got those weights from a few friends that I've still got in the business. But then you look at the pilot's weight and his briefcase and the third pilot seat, jump seat, things. You could have a weight reduction of over 3,000 pounds, which is 10 more passenger bags and coach seats. Looking more at the revenue seats, you look at load factor of the aircraft, the utilization factor, and at the $231 per hour block time, number of calendar years. Bottom line is that you could save $8 billion by doing this. American Airlines 2016 revenue was $40 billion and with a profit of $2.7 billion. So you can see how much that would increase their bottom line. Second opinion, this is from Aviation Week in September 2017. This is an analysis done by UBS Investment Bank for American, United, and others. They say that it would result in a $26 billion reduction in pilot-related cost, $3 billion saved in insurance cost due to improved safety. Believe that. $1 billion reduction due to better flight optimization. Not a question of if, but when, probably before 2040. Younger people are more favorably disposed to it. Americans are more favorably disposed. French and German less, at least. Before commercial flight, I would think that you'd do the cargo, air taxi, business jets, helicopters, and general aviation. I'd question general aviation. Jim, does that look familiar?
It does.
It's a caution warning system. Fault detection will err on the side of caution, resulting in false failure indications. The pilot's judgment's often called upon to avoid unnecessary precautionary landings and other actions. How would a pilotless aircraft deal with those alerts?
Computer can cover a lot more ground in evaluating actions or activities. The computer can cover a lot more ground and re-evaluate multiple times per second, much faster than a pilot can. So a computer would look at whatever warning came on and use another set of factors, or could be trained to use another set of factors to determine whether the warning was true or not.
Right.
There's also another side to that. A lot of times that master caution light will come on because of something that went, a slight glitch in the computer system. It doesn't, there's many times I've seen that caution warning light come on and just.
Because of the computer itself.
Exactly.
Yeah.
And so the computer's gonna be sitting there wondering why. And,
So they'd have to have a computer watching the computer.
you got,
Yeah.
something to redundancy, yes.
Yeah.
But there's still a lot of errors.
Yep.
But it's coming. And then, one thing he's not talking about yet, it's gonna come down to one pilot, before it ever gets to 0 pilots. There will be a
Step.
time that we will have only one pilot. Everybody remembers, 60, 70 years ago, we had 3 pilots in the cockpit. And, the automation was such that it went to 2 after a lot of fighting. It will go to 1 before they ever get to 0.
Yeah. So you had the navigator, you had the
It wasn't really a navigator,
pilot.
it was a flight engineer, because most of the things that he did were not systems that were available to the captain and the co-pilot.
All right, Jim, I'm hesitant to call on you, but go ahead.
Just remember, 2001 Space Odyssey, Al was the pilot.
It's been a long time since I've seen that. Need to get that back out. All right, so just things for discussion. Runway incursions, go-around decisions, loss of engine after liftoff, unexpected wind shear, anti-icing usage, pre-flight imperfections, diversion to non-automated airport. Icing is, I know a little bit about that. The windshields have de-icing systems in them, which is one of the costly things that would be eliminated. But you still got to worry about icing in that area and icing on the wings and other control surfaces, which are already heated in most cases. So there we go. And that's through the first session. And it's only 25 minutes into this. So I'm saying I probably went faster. We may get through all 10 sessions today. Oh, the previous, the flight, this class was snowed out. So that's, I think that was my niece at an earlier snow. It's the one that is at Maryland now. Session 2, we've already been through those. We've talked about this. And we've talked about the second opinion. So they were going to go through and analyze that analysis and what does the Airline Pilots Association say about that. They had 2 different action items that came out of that. So now we're going to look at specific events in which the pilot managed in an extreme emergency and saved passenger lives. You see the ones that he's got listed there. The first is U.S. Airways 1549. That was in January of 2009, and everybody remembers that one, I'm sure. That was when they landed on the Hudson. And you can see what's ahead as far as the agenda on the course. So they hit a flock of Canadian geese, lost both engines, and I think that's a pretty low probability. But if you're on that flight, it's 100%. The other thing I found odd, and I've always focused on the windshields, was that the geese hit both engines enough to knock them out, but they didn't hit the windshield. So I don't know how you could do that, but I spent a lot of time analyzing bird strikes and on the windshields, and that's the only thing that I knew that there was a problem with. Okay, so you can see that they took off at LaGuardia, and the whole flight time was 3 minutes and 32 seconds from the time he took off to the time he crash landed. We're going to see an NTSB video on this. It's only 3 or 4 minutes long, but listen for Sullenberger. The aircraft is Cactus 1549. One of the pilots also calls it 1529. So we'll go ahead and go into the video. There we go. See the speed left.
75 every day.
Here, Johnny 2760 is 5,000, turning your right to 150.
Johnny 2760, climb maintain 10,000.
10,000, Johnny 2760.
Jim, Hot 1 is the pilot.
Cactus 1549, turn left heading 270.
This is Cactus 1539. Hit birds to lost thrust on both engines, returning back towards LaGuardia.
Okay, you need to return to LaGuardia. Turn left heading up 220.
220.
Tower, stop your departure. It's got emergency returning. It's 1529. He bird strike. He lost all engine. He lost the thrust in the engines. He's returning immediately.
Cactus 1529. Which engines?
He lost thrust in both engines. He said.
Got it.
Cactus 1529. If we can get it for you, do you want to try to land 1013?
We're unable. We may end up in the Hudson.
Johnny 2760. Turn left 070.
070, Johnny 2760.
Hi, Cactus 1549. It's going to be left traffic to runway 31.
Unable.
Okay, what do you need to land? Cactus 1549. Runway 4 is available if you want to make left traffic to runway 4.
I'm not sure we make any runway. What's over to our right? Anything in New Jersey, maybe Teterboro?
Okay, yeah, off your right side is Teterboro Airport. Do you want to try to go to Teterboro?
Yes.
Teterboro, Empire, actually LaGuardia departure guy, emergency inbound. Hey, guys. Cactus 1529 over the George Washington Bridge wants to go to the airport right now.
Wants to go to our airport. Check. Does he need assistance?
Yes, it was a bird strike. Can I get him in for runway 1?
Runway 1, that's good.
Cactus 1529, turn right 280. You can land runway 1 at Teterboro.
We can't do it.
Okay, which runway would you like at Teterboro?
We're going to be in the Hudson.
I'm sorry, say again, Cactus?
Wrong answer.
All right. Kelly 2760, contact New York 126.8.
2068, Joey 276.
Cactus 1549, radar contact is lost. You also got Newark Airport up at 2 o'clock in about 7 miles. Eagle 5 4718, turn left thing 210.
210, 4718. I think he said he was going in the Hudson.
Cactus 1529, Houston. Cactus 1529, if you can, you got runway 29 available at Newark up at 2 o'clock in 7 miles. Eagle 5 4718, climb maintain 12000.
Okay, 1000 and even 5 until we hit.
Eagle 5 4718, I'm sorry, I missed that. Say again?
And we're up to 12,000 to it hit.
Okay, thank you. Eagle 5 4718, turn left 220.
220, 472.
Bring back any memories? Jim Holmes, any thoughts on that? You ever been in a similar situation to that?
Not a similar situation, no, but, my thoughts are like a lot of the pilots. The best thing he did wasn't necessarily his piloting skills, because I honestly think most pilots could do what he did. His best decision was to go there. There was absolutely nowhere else to go. If he'd have gone anywhere else, would not be anybody left to talk today, so.
Plus some people on the ground too, probably.
Exactly,
Yeah.
no doubt about that.
Yeah.
But he made the right decision, and he just did what his training, he had many, many years of training, and he executed his training, and it worked out great, But if he'd made the wrong decision, it would be completely different.
Yep. Yep. Any other thoughts? Okay, so what if this had been pilotless? Would it have turned back to try to land at LaGuardia? Would the decision be based on current wind measurements? What if the wind direction changed? Evaluation of the downside risk of all the options. Would the AFCS, there's a lot of acronyms in this stuff, and I know what they are, but I may not be able to remember them. Acronyms in engineering are it's a language all its own. I worked on the Patriot missile system, and when I started working, a guy gave me a manual that had 397 pages of acronyms. And it's like 20, 25 per page. And some of them are different depending on which, the acronyms aren't the same from one missile program to another. And some of them are, you got acronyms, but they mean something else. So it's a whole different world. So, which is safer, man or machine? We're not to that point. Hey.
In the case of landing in the river there, it's very possible, especially with the experience of this episode, it's very possible that can be programmed
Oh, yeah.
I think a better example of the dilemma would be, remember a couple of weeks ago, they celebrated in Britain the landing of the returning bomber that avoided landing in the field with the children and went on and crashed into the forest. Did any of you see that on the news?
I missed that.
Anyway, that evidently happened in the Second World War, killed all the crew, but evidently saved some kids that were playing
Yeah.
in the field or soccer field, whatever it was. So I think that's the kind of thing where a computer would have a hard time.
Right.
One of the big things is getting enough programming, getting the programming correct enough and granularity fine enough to do all the what ifs.
Right.
And that's a real challenge. It's only as good as what is put in the program.
Right. We're fairly close, I think.
Part of my experience with control systems is usually the key thing is the sensors and the information. You can program, if you've got enough computer capacity, program the computer to make all kinds of decisions and issue out control signals, but it has to have the right information coming in from the sensors. Those are the key things.
Right.
I think that they could provide a mechanism where plane could be transitioned to remote piloting. We do have drones anyway. And at least under a remote piloting scenario, they could turn on cameras and they could have the systems come up in front of the remote piloting, the remote operator who goes out.
Right. I mean, we've got drones that are operating on the other side of the world, operated by people here.
Yes, Falcon
So-
Air Force Base is operating drones
Right.
in Afghanistan.
Of course, those aren't loaded with 250, 300 people either.
No, but they're getting
But they're
close to real-time information.
right.
Now, the only reason it's not close to real-time is it takes time for receivers to transfer signals to the other side of the world. In the case of remote piloting, if you're in the same country, on the same continent with the aircraft that you're remotely piloting, you'd be within a second or two of in full communications with them.
Right.
Mike, I think it's less than a second or two. It's gotta be, because a whole second is a long time if you were traveling, the speeds of these aircraft, so it's gotta be a lot less than a second.
Right.
I see correlation with driverless cars. In some ways, airplanes are better. There's less hazards around.
Yeah, he'll get into that a little bit in that, we started off with the elevator. That's one dimension, up and down. Cars is 2 dimension. Airplanes is 3 dimensions. So it's
But you still have a lot of random things which you have to program in there. And this is what they're learning with your driverless cars is whether it can see a bicycle coming in at an angle where
Yeah.
one of the crashes, for instance.
right.
So these are the things that I see that it'll be a cyclical process to get there.
Right. Why don't we take a 5 or 10 minute break here, and we don't want to finish 10 sessions today anyway. Thanks. Well, this class has already been successful. We've generated some discussion. Why don't we go ahead and get started again? This machine thinks it's already better than man by designing the automatic flight control system It limits the pilot's control to the levels that the AFCS considers to be safe. That was Sully's comments after the flight. He said that the computer-imposed limits prevented him from achieving the optimum landing flare for the ditching, which would have softened the impact. Jim, do you see that? What do you think about that comment?
Well, you know, they say that it's a great landing if you can walk away from it.
That's what I always thought.
It's a good landing if you can walk away from it.
Yeah.
It's a great landing if the airplane can take off again. He made a good landing, he didn't make a great landing.
Yeah. If it had pontoons on it, maybe, but,
Yeah, well, he did a good job.
yep. But he was basically saying that he could have landed it better than the computer did, or helped. So, both man and machine have inputs. You got information coming into the processor, you've got mode control coming into the processor, and you've got output. The man, you've got 5 senses: sight, sound, touch, and smell. Those senses, the processors, the brain, you got the memory, intelligence, common sense, judgment, wisdom, situational awareness. You got the outputs, is the man's hand on the controls and the voice, and those inputs can control the control surfaces. So you've got the machine, you've got sensors, you've got processors, you've got actuators, and you've got the control surface. So you're getting to the same place. Sensors include the airspeed, gyros, accelerometers, altimeters, vertical speed, angle of attack, side slip. Navigation includes the GPS, the VOR, can't remember what that is right off. Is the visual operating restriction. The ILS is the instrument landing system. As far as warnings, the TCAS is traffic collision avoidance system. GPWS is ground proximity warning system. Jim could have probably told us what all those were right off. So the processors, you got 4-channel, redundant, self-monitoring, self-healing BAT. That's built-in test equipment. I remember that one. Actuators are redundant electrical, hydraulic, power supplies for the sensors, computers, displays, actuators. Today's flight control, you've got all those things that we discussed with the machine plus the man. One of my brother's contacts, which I mentioned before, was Wally, who's the A-20 captain. He says, I'm a guy who monitors an autopilot for a living. Fully automated flight control, fully automated automatic flight control system. He says that's a new acronym. Would eliminate that information from the pilot. So we're already into session 3. If you take away our traditional ways, you must replace them with something of value. That's somebody's proverb, Something of Value by Robert Rourke. So we're back to that. what things of value must be added in the machine to make it as good as the man, Captain Sullenberger. So again, we've got the man. Okay. So what did Sullenberger see, hear, identify, and decide? What about hands? What did he use his hands for? Controlling the aircraft. We'll just go to the next slide. You can see what he had, the man in this case. Under sight, he spotted a flat, unobstructed area, which Jim mentioned earlier. That was the key. And he had a memory of the area. He made the safest decision based on downside risk. So we've been over that. Saying that the hands are almost inessential in today's control system. Got electro-hydraulic actuators. It's already controlled by the autopilot, by the computers. May be necessary to add auto takeoff mode to the autopilot. So that's an A-20 landing gear panel. Not a lot to it, up and down. Reminds me of the remote on my fireplace, gas fireplace. How can we replace the hands? No replacement needed as far as the side stick. Existing servos are adequate. Possible minor mods to the computer to add mode. Hearing. How might we replace the human ears and voice? Air traffic control could be easily transmitted electronically, not orally. Could be done by a human air traffic control operator, or in the future, fully automated air traffic control. That's another thing to consider. Every electronic system, old and new, must be made invulnerable to electronic warfare, terrorist actions, which would be another difficult problem. I don't know how we make it's hard enough to make our current systems on the ground meet that requirement. Sight. How would we replace the human sight? Emergency landing assessment requires new sensors, artificial intelligence. Could it be all weather to detect runway incursions for routine landings? Brain memory of the area. We've talked about that. How might we replace the human brain? Computer memory for every possible emergency landing spot within the airline's service area. Continuous flight path calculations. Instant prioritization of alternatives based on current aircraft weight, energy vectors, condition, wind, fuel. Automatic aircraft configuration control for approach and landing selected at the selected alternative. What else have you thought about as far as 1549? Here's some ideas. Bird flock detector. Bird flock inhibitor. Say what? Yeah. Yeah, he's got a sense of humor. Based on preceding material, it seems unlikely that existing flight control technology could have saved Flight 1549. 1549 wasn't a routine flight. I don't think it's routine flights that you got to worry about. So, would today's automated control technology be adequately safe for routine pilotless flights? If so, then the engineers could focus on non-routine events. Talking about the resources, NTSB accident reports and NASA's aviation system safety reporting system. Okay, so that's the summary of what we've talked about so far. So then at the bottom, you know, we're saying that looking at 1549 without emergency action, current technology is close to being adequate for routine flight, but throughout this course we'll look at other events. So let's leave the open discussion and reserve judgment. Okay, so we've got 4 videos. It's going to take me a while because I didn't know that we would get this far into this. I'm going to need to take these to our operator. I'll be right back. Hey, let's see some light here. Okay, on that
Condor 597.
597, you go to refinery, continue right and heading 100, stay clear NDB deep. Approach runway 08 right.
Condor 597, right heading 100, cleared ADB DME, it's a right. Das ist eine Meile links von weg.
The latest aviation runway 08 right, landing direction 1600, 1700, 1900 and 1800 meters and vertical visibility is 2000 sensitive for ADB.
Understand this?
So vertical visibility, say again?
According to ARTIS, the vertical visibility is 2000 meters.
Should be okay.
Roger.
Okay.
Okay.
Also 1200 Meter bräuchten wir.
Ja.
Das war immer drüber. Wollen wir reduzieren?
Ja, Flaps 1.
Flaps 1. Speed steht noch auf 220. So, jetzt noch 6 Meilen zum Descent Point.
Mhm.
Das ist 16 Knoten Tailwind, ne?
Ja. Flaps 2.
Flaps 2.
3 Grad drehe ich ein.
597, the ILS on runway 08 right is working now. Do you want to continue the ILS approach runway 08 right or continue ADB?
Condor 597, continue on the ILS.
597, so you're re-cleared for the ILS approach runway 08 right.
Condor 597 cleared ILS 08 right. So, ich gebe da jetzt noch mal kurz das ILS ein.
Ja.
Okay.
Okay.
Wir räumen das auch auf.
Gear down.
Gear down. Dann haben wir nämlich kein Getue da unten,
Genau.
wenn die Sicht dann doch runtergeht.
597, contact tower 1205, schönen Tag.
Condor 597, 1205. Danke, Herr, tschüss.
Flaps 2.
Flaps 3. München Tower, grüß Gott.
Condor 597 established ILS 8 right.
Condor 597, grüß Gott. One departure in front, wind 080 degrees, 4 knots.
Roger.
Flaps full.
Flaps full.
Landing checklist.
Landing all green, flaps full.
All green, flaps full.
11, 12 Knoten von hinten.
Mhm. Und Manual Flight.
Die Sicht wird unten dann nochmal weggehen wahrscheinlich.
Condor 597, wind 080 degrees, 4 knots, 8 right, clear to land.
Condor 597, clear to land, 08 right.
Der soll noch gut nach vorne drehen.
Ja, letzten Moment dann. Moment noch 4 Knoten Tailwind.
Mhm.
300.
100 above.
Runway inside.
200.
Minimum, continue. Zwei Knoten von hinten.
50, 40, 30,
Manual brakes.
Jo. $70. Off control.
You have control.
Deutsche Zeit 1 Stunde vor. Es ist jetzt 10:30 Uhr.
Super Landung.
Dankeschön. Service Condor 597 vacated. Bravo 7.
Condor 597, continue taxi Bravo 7, Sierra 6, hold short of Sierra.
Condor 597 holding short Sierra to Sierra 6. Das geht erstmal geradeaus.
Condor 597 is cleared to cross Sierra and contact apron 121-775. Ciao.
Condor 597, 11775 and clear to cross Sierra. Servus. Apron is got Condor 597 approaching Sierra 6.
Conda 597, grüß Gott. Taxi distance 105, Charlie 4 and Oscar 1.
Condor 597, 105 via Charlie 4 and Oscar 1. Charlie 4 ist der nächste rechts.
Okay.
Wolltest du die APU mit anhaben?
Machst du mal wieder an. So, dafür sind wir um 2.50 Uhr aufgestanden.
Genau.
Naja.
Aber es ist wenigstens noch hell.
Und das Alpenpanorama war es wert.
Das stimmt allerdings. Allemal.
LP 1764, ready, 107 Bravo.
Ob wir uns schämen oder nicht schämen.
LP 1764, Roger, so when clear of crossing Conda 320 right left, push approved, facing stop.
Der erste hinter dem Terminal ist dann unserer.
Jo.
Clear of Condor, cross behind, push
Und
back,
APU
is
ist da.
approved. Face to south, confirm?
This is correct, facing south.
Recht frei. Und 320 steht dran.
LP 1764, requesting.
LTU 1764, taxi Charlie 2 and Whiskey 1, Sierra 5.
Charlie 2, Whiskey 1 to Sierra 5, LP 1764.
Brakes hot.
Jo.
München Air, English good, Berlin 137, position 1 up on request push back.
Berlin 137, grüß Gott, push approved, north orange line.
Push approved, north orange, 137.
Cabin 7 orders in park.
Parking checklist.
Okay, so the point here is what did they do that couldn't be replaced by a machine? Yeah. Right. That would definitely be an obstacle to pilotless flight. In some cases, the computer could make a better decision than the pilot, but in this case, I'm not sure. Okay, so going back to the senses, you can see that how it's used in the control, monitoring, configuration, and communication. Brain being used in all of them. Okay. It's actually, all right, here we go. Here's the second video.
Là, il est actif, c'est bon. On approche. Là, il se trouve 4-3 single. Deuxième AP, 4-3 dual, AP 1 plus 2. Volet 2.
Descend on the glide path from 823 right, and the latest IVR readings, touchdown 550 meters, midpoint 250 meters, stop end 500 meters.
La vitesse managée, et on a dit qu'il fallait être stable à 1300 pieds.
Not a lot going on here.
T'es train sur sortie.
165.
Volet 3.
2000.
We'll eventually get there.
Speed. Mid. And coming down.
Everybody stay awake.
Donc le prochain step, c'est le call-out à 1000 pieds normalement.
Yeah. I don't remember this one.
Stabilisé. Le prochain step, ce sera un call à 500 pieds. Les packs, tu veux les mettre? 500. Alors ensuite, on attend le land à 350 pieds. 400.
Busy?
Land. Je commence à regarder dehors. 300. La
Where are you
rencontre.
seeing that? Huh? Okay, all right.
200.
Oh, there we go. We're getting there.
100 above. 100.
That's good because it's real.
50, 40, 30. Minimum. 10. Retard. Retard. Spoiler. Voilà, là, je vais désarmer la petite.
Not sure that it was in use at that, probably was. when this was done. Not me either.
C'est là, hein, je pense. Hein. De toute façon, si elle est allumée, c'est que c'est ça.
Advance on 668. Yes, it's coming up on your right-hand side now.
Okay, so that was at Manchester. That was another Airbus, 321. Here we go. This one you can see the pilots. All English. Pilot and co-pilot sometimes aren't communicating that way.
1,000.
I think this one's a Boeing aircraft, isn't it, Jim? In that one? Those are heads-up displays that are in front of them there.
500.
Lights.
100. 50, 40, 30, 20, 10.
Okay, we'll get one more in. Jim, you ever fly into Anchorage?
Approaching minimums. Minimums.
See in the upper right corner, those are pilot assist handles.
50, 30, 20, 10.
All right, so we'll stop there. Still got 300 more slides to show you, but we'll stop. So did the discussion today change anybody's mind? Nope, still no. Still no. No, nope, all right, got it.
Still maybe. I'm waiting to see how many more sensors there are.
Right, right. So the other thing is, and I realize that my presentation skills aren't as good as wrestlers in everyday engineering or Michael's in what he presented last week. But what do you think? Is this worth presenting as a class at Ollie? I mean, be honest, because it's nothing, I'm not pushing from a personal point of view to do it, but.
Well, for 10 sessions, 2 each week, you're going to have to get into it in pretty good detail to show what this is.
Yeah, I'm thinking that too. Of course, the class was designed, I think, as a round table with everybody sitting around instead of in an auditorium. But I think you'd probably get more discussion that way. John?
Was this a class of Ollie?
Yes. Yeah, it was Ollie at Duke.
But it wasn't a group of people that had some knowledge.
No, but I think that a lot of the people that signed up for it because of interest had aircraft knowledge.
I would be interested in doing it, but I don't know how. Probably wouldn't be very many people in Ollie.
Right. Right. Okay, well, I really appreciate y'all coming today and coming to the rest of the classes. Michael's got it next week. I'm going to be at the beach, so it'll be raining, but I'll be there. Anyway, so what are you presenting next week?
Next week, the title of the class is Will That Tree Fall on My House? And we're going to learn how to measure things without having access to them. We're going to learn how to use our own bodies as measuring systems. And we're going to have, for the second half of the class, we're going to have practical exercise. And if the weather is okay, we'll do the practical exercise outside. If the weather is not okay, we will do the practical exercise inside, and I'll talk to the museum about that. And you will do such things as measure the height of the ceiling in the museum and the height of the columns in the museum. And we'll talk about how to measure things when you don't have any measuring tools with you.
Does that bill require us to use math?
Math?
Might require you to use numbers.
Not any more than the 4 basic math skills, okay?
Will we need a chainsaw or be able to climb a tree?
No, no. It would be helpful if you brought a pencil or a ruler with you, just something, but it doesn't have to have any, it can be anything straight that you might use to cite things with. It would be very interesting, you know, for example, I know that probably one tree in your yard, in everybody's yard, unless you have a clear-cut yard. There's one tree that you have viewed with some sort of skepticism.
My neighbor's got one that I'm really worried about.
Well, believe it or not, you can figure out whether your neighbor's tree will fall in your yard without going over there.
I don't mind going over there.
Okay, well.
All right.
You will be able to figure out whether that tree will land on your house or in your yard.
All right, good.
Okay?
I'll take good notes for you then.
All right, that's good, good. Take a video if you would. All right, guys, I appreciate it. Thank you so much. I bet.